Today, I'm standing. I live in a city that vibrates with life. A city of art, history, science, and projects. Projects. I have projects. To turn them into reality, I need to get out and immerse myself in the city. I need to see, sense, breathe, connect. That's what changed my life. Being able to stand or sit at will, to stride, blend with people, wander with my friends, and talk with them at eye level. Three years back, I met Nicolas, who offered, "How would you like to stand up and go for a walk?" At first, I did not believe him. But today, I'm standing.
Wow, what an incredibly inspiring example of physical AI. Hi everyone, and welcome to AIM117, which is all about building physical AI with NVIDIA on AWS. I'm Sean Kirby, and I'm a principal cloud architect in our AWS Professional Services organization. And I'm joined today by my colleagues Ali Shalrakni from NVIDIA and Abhishek Srivastava, also from AWS. We have a fun-filled and packed agenda for you here today. I wanted to start off with just a quick survey. Show of hands, how many of you already have physical AI programs underway? Any folks? Okay, I see a couple of hands there. Another show of hands, how many people are considering launching into a physical AI program in the next 6 months or so? Okay, some more hands. Well, we've got something for everyone here today. We're going to start off with a survey of physical AI, what it is, and the tremendous potential that it offers. We're then going to talk about what we view as the 5 key pillars for accelerating your physical AI programs, how to get started and how to meet some of the challenges that you may be facing. We'll talk about a number of proven technologies from NVIDIA on AWS that will help you with your programs. We'll then go into a particular example where we've used these very architecture patterns and these technologies to create a humanoid stock-keeping robot. And we'll include many of the best practices and lessons learned that we've gathered along the way. So, first of all, what is physical AI? Well, put simply, physical AI is the embodiment of artificial intelligence in any physical object or smart object. Probably most of us think of robots when we think of physical AI, and that's certainly one of the greatest examples. However, physical AI extends far beyond robots to anything in the physical world, from smart machines to assembly lines in a factory, to even a whole smart factory, or even a smart municipality with smart buildings and connected infrastructure and vehicles. All of these are part of physical AI systems. And at the heart of physical AI is a world foundation model, very similar to the models that have given rise to so much of the popular generative AI today. However, these models usually incorporate a vast array of different types of input. They're very multimodal. So in addition to some language instruction inputs and maybe some video or photos for context, they can take all kinds of other physical data, temperature, humidity, force feedback sensor data, etc. And they combine all of that into an output that then instructs the physical object how to behave and to perform sophisticated behaviors. And the nice thing about these models is that they incorporate a lot of knowledge about the physical world, and they generalize very well so that you can fine-tune them to your particular domains and expect them to do a variety of tasks. They're also very good at adapting quickly to different embodiments. So different types of humanoids, for example, doesn't take nearly as much training as has been invested in the initial World Foundation model. And we're going to talk about some examples like NVIDIA Isaac GR00T, for example, and how to run that in the cloud. So what is the impact of all this physical AI? Well, one of the key industries, I think, that comes to mind when we think about physical AI is the manufacturing and the associated supply chain and logistics, making and delivering physical goods throughout the world. There are over 10 million factories, 200,000 warehouses, 1.5 billion cars and trucks that are all part of this complex industry. And every one of them stands to benefit from physical AI. So the potential is enormous in that industry, but it extends to all industries, including healthcare, agriculture, retail, and the public sector and beyond. NVIDIA CEO Jensen Huang has stated that 65% of the global GDP across industries can be improved by physical AI. This is a staggering more than $50 trillion of economic impact. But physical AI isn't just some pipe dream out in the future. Physical AI is here today. In fact, at Amazon, we're using physical AI in many of our robots in our warehouses and distribution centers. Pictured here is Vulcan. This is our first robot with a sense of touch. And Vulcan was born out of the desire to help our stock keeping workers to reach both the highest bins on a rack and the lowest bins as well. And in order to do so, it needs a multi-sensory, multimodal input into these foundation models. It needs to be able to see where there's space in an existing bin, and it needs to be able to have some feedback as it's handling all different kinds of objects, different shapes and sizes and textures. And so we've incorporated a force feedback mechanism to give it that sense of touch. All this multimodal data goes into a physical AI model that was trained with many of the patterns we're going to show you here today. And so now in operation, it's saving our employees up to 1.5 hours a day, not having to go up and down a ladder, and also making their jobs a lot safer and more enjoyable as they don't have to bend over all the time, putting a lot of undue stress on the lower back. Well, that's not the only place that we're using physical AI. Another robot that we use is part of our zero-touch manufacturing initiative. And we're using this robot arm for the product inspection and auditing stage for all of our Amazon products. And of course, we're always coming out with new products, and so we need to be able to introduce those products into this zero-touch station without bringing production to a halt. And so we need to train these robots to handle these new products in simulation. And this is part of our Simulation First initiative, which is a very important part of the 5 pillars that we're going to be talking about to really help accelerate physical AI. What we do in this case, for example, is we can bring in a CAD design for the packaging and for the new product itself, and then using NVIDIA Cosmos on AWS Batch, we're able to generate, what we do is we generate 50,000 variations of that CAD specification so that we can train the robot through simulation to handle that new product. And with a zero-shot deployment, that robot is able to handle the new product and manipulate it, as you see here in the animation, without bringing the line down. That's not the only place we're using AI here with this robot. We actually also bring in all of the product specs. And using Amazon Bedrock behind the scenes with some large language models, we interpret those specifications to understand what kinds of testing do we need to do on this product, what really constitutes the necessary auditing. And so all of that is automated as we introduce these new products into a true zero-touch manufacturing initiative. Well, what's required fundamentally to achieve this kind of physical AI? We believe there are 5 pillars, and the first is data. Training this kind of sophisticated behavior requires an enormous volume of very high quality and realistic data. Some of this data is generated today by humans through teleoperation and examples that robots can be trained to emulate, but the vast majority will be generated synthetically in the future because it's just impractical. The next pillar is around training. It's taking all of that data, and there are many applications for training, from fine-tuning a world foundation model to your particular industry or domain, to training a model through imitation learning or reinforcement learning, and training a policy for robots to execute particular advanced and sophisticated tasks. The next pillar is simulation, and this is again part of our sim-first approach. We test these trained models extensively in a simulated environment before deploying to the real world. This is both a lot safer and less time-consuming, and less costly as well, because we don't have accidents with robots and the expensive equipment that they're ultimately deployed onto. The fourth pillar is what we call sim to real, and this is where we have gone through a cycle of simulation and training and gotten to a good result. Now we need to really test this in the real world. This is literally where the rubber meets the road. And as you're developing more and more sophisticated physical AI, you're going to be deploying this to more and more different types of objects, maybe in a manufacturing setting, different types of machines, in different locations around the world, and every one may have a different version of the model, a different type of device, and so forth. And so managing your fleet of physical AI smart devices becomes a challenge. And we have some technologies, including AWS IoT Greengrass, to help you manage this complexity. The fifth and final pillar is agentic orchestration. And this is where we bring together modular building blocks of physical AI. Not only does this provide good separation of concerns, but it also provides you with reusable elements. And frankly, it's an essential element to achieve long-running and very sophisticated behaviors, like fulfilling an order all the way from order placement to the shipment of that order and all of the picking and packing and logistical operations that need to take place in between. You're going to see how we've used this pillar in the example of the Humanoid that we built a little bit later on in this talk. So these 5 pillars are by no means meant to be part of a waterfall cascade approach. Once you've been through all the 5, you're good to go, move on to the next problem. Instead, they form part of a virtuous cycle, a highly iterative process in what we call the physical AI flywheel. You start off with your data, and you do some training, and then you test that trained model in simulation, deploy it to the real world, and then you gain some feedback from that and additional data based on that real world testing that you can then feed back into further training and so forth. And so we go around and around the flywheel loop until we achieve the level of sophistication and quality for physical AI that's required. Now that said, there are still plenty of challenges that I'm sure many of you may be thinking about or already facing in this, and we're going to show you how these NVIDIA technologies on AWS can help you meet these challenges. The first is the high volume of data. In the Humanoid example, just the simple task of picking a bag of potato chips and putting it in a box requires at least 800 examples in order to be able to learn that through imitation learning. More sophisticated behaviors could take thousands or even millions of examples. And the only way to really achieve that is through synthetic data generation. Another challenge is simulation accuracy. And this really helps to close the sim to real gap. You need not only a realistic environment with photorealistic surroundings and so forth, but very realistic physics, which is a complex topic. And that's something NVIDIA together with AWS can help you achieve. Now, all these tools are very sophisticated. They've got a lot of ingenuity built in, and to really get the most out of them, you really have to know how to deploy them most effectively. So there's some complexity in the setup of this. And we're going to show you how through things like NVIDIA NIMs, for example, we can pre-package that into a distribution that you can spin up and get working quickly, shortcutting all of that complexity. And that also leads to increased repeatability and collaboration. You might be facing some challenges with different teams working around the world in different standards and so forth. This is a little bit of a Wild West right now in the physical AI world, but we'll show you how to standardize this so that you can share and collaborate more easily. Then there's time to results. These models are pretty sophisticated and they take a very long time to train on a single instance. And so you really need to think about multi-GPU and multi-node parallelization. And that can be a complex topic. But here again, we're bringing some proven patterns. We're going to go into more detail with you here as to how you can get your multi-node simulation, your multi-node training jobs up and running very quickly. And then of course, cost effectiveness, trying to do this on a fleet of instances yourself on-premise can be very costly and probably not fully utilized unless you have a truly massive physical AI program. So doing this in the cloud gives you all the benefits of elasticity and cost effectiveness. And then we talked about fleet management. Last but not least here, as you begin to deploy to more and more smart devices, you need a single pane of glass to manage these very effectively. So those are the challenges. We're going to be diving deep into each of these pillars with various solutions for these. You can see some of them here, but I want to make sure our colleagues have enough time to go into the details and also share this example with you. So without further ado, I'm going to pass to my colleague Ali to take you into a deep dive in these incredible NVIDIA technologies.
Thank you very much. Hi all. I'm Ali Sharakni. I'm a developer relations manager at NVIDIA, focusing on the robotics ecosystem at AWS. I hope we all agree that we have entered the era of physical AI. Autonomous vehicles and robots have been around for decades, but something fundamental has recently shifted. And that's moving from arrays of sophisticated, specialized models into a unified model that performs end-to-end understanding of physical AI. And one key enabler for that is what we call the three-computer framework. Let me walk you through this. So first, we need to train a robotic foundation model on the cloud using, for example, the P instances on AWS. That would enable us to develop large foundation models for robotics and use massive scale data sets to train those. And then the other computer that we need is for simulation and synthesis of data that is used to train those models. And that's what you can use like other sophisticated RTX Pro servers on AWS to synthesize data and train models and test those on the cloud. And then the last computer is actually the brain of the robot that is deployed on the edge. And for that, you can use AGX computers and deploy the trained models that are optimized for edge deployment on the cloud. And those would process real sensory data on the edge in real time and perform actions respectively. Right. So, but there is a significant data gap when it comes to physical AI. Unlike large language models that can leverage internet-scale data, robotic systems face severe data scarcity. We need thousands of human demonstrations, as Sean mentioned, to train a simple manipulation task, and that does not scale, and it's not feasible. So what we can use is instead to use a handful of real data and to augment those using synthetic data to generate diverse and edge cases for robotic training. So you can use teleoperation to collect the initial seed of training data using manual demonstrations. And then you can use Isaac Sim and Isaac Lab to generate variations of those using realistic scenarios, realistic trajectories, and add variations of the scene. Gurut Mimic from Isaac family of models can actually be used to create those trajectories for you, and Isaac Sim would add the variations to the scene. So what we are delivering here is quite simple. We are using real-world data and augmenting those by adding domain randomization into the scene. So let's dive deeper into this. This is the data that you need for training realistic physical AI applications. At the top, we have real-world data that is high quality, but it's hard to capture, and it's not scalable. But then you have synthetic data that is not as high quality as real data because it doesn't capture a lot of the nuances of physical interactions and dynamics, but it's very scalable. But at the bottom, you have inter-level data, which is not really usable for robotics applications. For example, if you have a video of someone picking up an object, it doesn't give you the tactile feedback or the force dynamics or the mechanical interactions that you need to train a robot. So we need a hybrid approach here that would take a small amount of real-world data and would amplify it and diversify it using domain randomization and real physics simulation. Right. So you can leverage Cosmos family of world foundation models to bridge that data gap. This is an open source set of models from NVIDIA that is available on AWS and on GitHub. And in those family of models, we have Cosmos Predict that allows you to generate up to 30 seconds of video that would describe what happens next. And we also have Cosmos Transfer that would allow you to generate photorealistic scenarios by varying lighting conditions, background, the environment, and the weather, etc. And we also have Cosmos Reason, which is a vision language model that is trained for physical interactions, and it can support human-like thinking. Here is an example of leveraging Cosmos Transfer in combination with Isaac Sim and NVIDIA Omniverse. NVIDIA Omniverse provides you the physical accuracy of the real world, the physics part of it, the simulation of the robot, and the 3D assets and the interaction that happens between those. But then you can leverage Cosmos Transfer to inject diversity and domain randomization into the scene and create very realistic scenes that would help you amplify your training data set for your robotics applications. Another way to create synthetic data is to use dreams. This is Groot Dreams from NVIDIA that would allow you to use a single image and a text prompt to generate robotics trajectories that would be then used to train your physical AI models. So you can just provide a simple text prompt and use Cosmos Predict to create a future scenario based on your text prompt and single image input, and then use Cosmos Reason to label the data and create the trajectories that you need and validate those as well. Right. So let's take a look at the end-to-end pipeline for a sim-first approach for physical AI development. So on the left, you have your training data, and that can be text, image, videos, teleop data, or simulation data. And then you have at the top, you have your foundation model training pipeline where you have a model architecture, and then you train those and validate it and optimize it for deployment. And that's your perception model. But for robotics application and physical AI, you also need you need the robot to interact with the physical world. So just the perception is not good enough. So at the bottom, that's what you have, is robot learning. And it's where you train the model in simulation using the perception model as well as your synthetic training data to train the policies that would allow the robot to interact with the physical world. But that's not a single-shot training. This actually works as a virtuous cycle where the VLA would then use the demonstrations from the robot to improve itself, and then it's fed back to the loop, and that's how the robot would be trained, and the VLA would be trained together to meet the KPIs for deployment. And finally, you can also test and validate all of that in simulation as well. So you can have your test data as well in simulation, and as a fleet, not a single unit, and test the whole pipeline. So the whole thing, the amazing thing about this is that you do the entire robot training and the perception training in simulation without doing anything in the real world. That would save you a lot of time and money in terms of prototyping and testing on real hardware. Right, so just double-clicking on the learning part and the training parts, you can, for the robotics part of it, you can use different types of data together with Isaac Lab for the reinforcement learning or imitation learning. And then you can use Isaac Sim and Cosmos for synthetic data generation and software testing in the loop. And while that cycle is done and your model is trained, you can then deploy that to the edge on Jetson Tor for various applications like humanoid manipulation or autonomous mobile robots. For humanoid specifically, you can leverage the generalized humanoid robot model from NVIDIA, GR00T N1.5. That is an open source model and is available on Hugging Face and on AWS. That would enable a two-system architecture for thinking fast and slow. The system 2 is for reasoning and understanding, and system 1 is for fast thinking and fast reactions. And it also supports cross-embodiments. Once you have generated all your synthetic data and trained your robot policies and perception models, you're now ready to deploy the robot to the edge. And for that, you're going to need also a very performant, ultra-high computer to be able to do interactions with the real world and fleet management. So Tor is a good candidate for that. And here are some of the early customers that we have engaged with. So it can be used for humanoid robots, for multimodal AI and perception interactions. You can use it for visual agents, which allows you to generate custom alerts and video summarizations in warehouse environments, for example. For medical robotics and instrumentation, where you need real-time streaming and inference, Tor provides great compute power for that, with over 2,000 TOPS of compute. And also for autonomous robots and machines, where you need simultaneous localization and mapping, or navigation for agriculture, for example. Tor is a great computer for those. And for high performance computing and inference, where you need high bandwidth and high quality images, again, Tor has great I/O throughput for those applications. And with that, I'm going to pass it to my colleague Abhishek, who is going to talk you through some great use cases for humanoid robotics. Thank you.
Thanks, Ollie. Good morning, everybody. I hope you enjoyed the session thus far. I'm Abhishek Srivastav, Principal Solutions Architect, AWS. For the remaining of the presentation, I'm going to go through the exciting collaboration between NVIDIA and AWS in advancing the physical AI. But before I go deeper, I would like to bring the same slide once again. This is what a complete ecosystem looks like. 5 pillars of physical AI: data, training, simulation, sim-to-real, and agentic orchestration. And across each of them, NVIDIA and AWS is offering a unified solution for our customers. Keep these pillars in mind. As I move forward, I'll cover the integration architecture, as well as the making of a humanoid robot for a supply chain operation. So let's start with the data pillar, the foundation of physical AI. Training a humanoid robot requires a massive amount of synthetic data. And as we learn, capturing the data from a real world is really time and a resource intensive. This is where NVIDIA Cosmos World Foundation model on AWS can help our customers. So when we are making a humanoid robot for our demo, we followed a 3-step process. In step 1, we captured 800 episodes of human teleoperated data, performing a pick-and-place operation in a real world for a single environment. This is the ground truth, and it sets the baseline of how a successful operation looks like in a real world. We then use that data, the human teleoperated data, to train Cosmos Predict World Foundation model on AWS batch at scale. Using this fine-tuned Cosmos Predict World Foundation model, we augmented the data sets to create a future world state of the videos, and that completes how a new synthetic data looks like in the physical world. In the second step, we augmented the data set using Cosmos Transfer to create diversity such as material and lighting conditions. We then use Cosmos Transfer in the final step to evaluate and filter the synthetic data that is generated. Just so you know, with the 16 hours of human demonstration, we have created more than 1,000 scenarios of synthetic data that would have taken for us almost 4 months to train the humanoid robot for a supply chain operations. So let's go deeper and learn about the deployment architecture in AWS. We have chosen Amazon EKS to deploy, which is a fully managed Kubernetes service to deploy Cosmos Predict foundation model on AWS. EKS scales across multiple nodes based on the inference volume while still managing the control plane availability. One of the key benefits of this architecture is total cost of ownership optimization, the TCO optimizations. NIMS containers are pre-optimized for a high inference volumes, whereas EKS offers a dynamic scaling and pay-as-you-go model that is required for the optimum compute utilization and reduce overall cost of training. For our human demonstration, we have used P5 4x large EC2 instance, each of them powered by NVIDIA H100 Tensor Core GPU with 256 GB of system memory and 80 GB of GPU memory, just sufficient to run Cosmos Predict on AWS. We are leveraging Amazon Elastic File System, EFS, to store the generated synthetic data out of Cosmos model and CloudWatch to monitor the cluster performance as well as the job inference attributes. If you like to go deeper into learning how to deploy NVIDIA Cosmos models on AWS, I would highly encourage you to check out our detailed blog post. Let's dive into the training pillar of physical AI. This is where you teach the policy to interact with the physical world. There are two key approaches when it comes to training a robot: reinforcement learning and imitation learning. Reinforcement learning is like training by trial and errors. Imagine a humanoid robot walking in a complex environment. Each time the robot takes a stable step forward, you give a positive reward, and when it stumbles, you provide a negative feedback. This approach is extremely important when it comes to introducing an adaptive behavior within a robot, like locomotion policy. On the other hand, the imitation learning is like teaching by an example. So as a human, you demonstrate an example, and the robot is going to observe the demonstration and imitate the movement. This type, the imitation learning, is very effective when it comes to performing a manipulative task, like pick and place operations. But in practice, when you are building a complex physical AI system, we normally use a combination of both reinforcement learning as well as imitation learning. Now let's explore the architecture for training pipeline on AWS. we have made this really simple for our customer. So we have a common architecture to run NVIDIA Isaac Lab for reinforcement learning and NVIDIA GR00T N1 Open Foundation model on AWS for imitation learning use cases. At the center of this architecture, what you see here is AWS Batch, which orchestrates the training as well as the fine-tuning across distributed compute resources. Batch is a fully managed serverless batch service that offers a pay-as-you-go operating model, which is really effective for your cost-optimized training on cloud. Using Amazon Elastic Container Service, you can deploy Isaac Lab or NVIDIA GR00T containers across multiple node and multiple GPU at scale. Amazon EFS serves as a persistent storage across distributed node for storing the checkpoints of training policy. And finally, CloudWatch provides a real-time monitoring of training jobs like loss curves and learning rates. For more details, you can follow the step-by-step guide of running NVIDIA Isaac Lab on AWS in the QR code. Let's talk about simulation pillar, a critical component of validating a trained policy in a virtual environment. Simulation provides a virtual environment to validate a robot behavior before you deploy them in a real world. We can test thousands of scenarios in parallel with a different lighting and material conditions, object placement, as well as including some of the edge cases, which is really hard and impractical to replicate in a real world scenarios. This is where NVIDIA Isaac Sim on Amazon EC2 helps our customers to deploy simulation environment quickly on AWS. Isaac Sim is a physically accurate, photorealistic simulation platform built on NVIDIA Omniverse. You can simulate physical world dynamics such as friction, gravity, collision, etc. A great example of a simulation is training our own humanoid robot in a virtual AWS Expo floor with thousands of virtual attendees, different carpet and flooring conditions to ensure it works before we brought them into reInvent. And like that, you can simulate various environments such as warehouse, factory floors, healthcare facilities, and many more. Now, traditionally, running Isaac Sim require high-end RTX workstations on-premise. It is hard to set up, and it is constrained by the physical capacity of your physical server. We made NVIDIA Isaac Sim deployment on AWS really simple for our customer. AWS Marketplace offers a fully configured AMI to run NVIDIA Isaac Sim workstation for both Windows and Linux environment. You can deploy Isaac Sim in a few clicks over hundreds of EC2 environment powered by NVIDIA GPUs. So you can get started to validate within few hours than few weeks. Let's discuss sim to real. Now here is the reality. Sometimes the model that works in simulation does not effectively perform in the real world. And this is called reality gap. Different factors such as physics accuracies, sensors noise, as well as the environment variations can impact the performance of a policy in a real world. Closing this reality gap is an ongoing science that requires you to bring in a human feedback in the training loop. With every iteration, you need to transfer the model from cloud to edge devices, manage the deployment fleet, and as well as over-the-air deployment and updates. This is where AWS IoT services can help our customers to manage the communications and handle the deployment from cloud to physical robot. So let's explore the architecture. AWS IoT core service offers an edge to cloud communication hub. IoT core establishes a secure bidirectional communication to offer a command back to your robot as well as the telemetry data back to the cloud. Amazon SageMaker model registry offers you a centralized repository to store, version, and manage the physical AI models. And AWS IoT Greengrass v2 facilitate the model and component deployment to the edge devices. For more details, please do check out our blog to deploy robot using IoT Greengrass v2. Let's discuss the final pillar, which is the most exciting one, agentic orchestration, which transform a robot to handle the intelligent generic task. Physical AI evolved from a specialized to a generalist robot. A specialized robot follow a rule-based logic, but the generalist, like Humanoid, requires cognitive reasoning ability to respond and operate in a dynamic environment. Things like goal understanding, path planning, task decompositions, each of them are really complex tasks to process. But using Amazon Bedrock Agent Core, customer can build these atomic AI agent at scale for a physical AI system. Let's dive into the architecture diagram for agentic orchestration. At the core of this architecture, we have Amazon Bedrock Agent Core for building, deploying, and operating the AI agents at scale. Bedrock Agent Core can help to build a modular AI agents for functions such as inventory planning, task decompositions, path planning, and SKU identification, and many more. For the humanoid robot that you will see in few minutes, we have used the Bedrock Agent Core with a fine-tuned NOAA Lite foundation model to do a task validation. So every time the robot picks an item from the table, we validate if the operation is successful, otherwise provide a dynamic signal for the next step. The architecture is fully scalable. From a single robot to a wide fleet automation, Bedrock Agent Core provides an intelligent layer that transforms a physical automation to a physical AI. Let me walk you through top 5 reasons why you should be choosing for in AWS and NVIDIA for your physical AI journey. First, scalable infrastructure. Physical AI development requires scalable infrastructure for both training as well as simulation. The training that used to take weeks now takes hours using AWS infrastructure. Second, a complete physical AI ecosystem. NVIDIA and AWS have fundamentally changed and reshaped the stages of physical AI development, from the data curation to the model training to a photorealistic simulation and agentic orchestration. Across each of this pillar, we are offering a unified solution across all industries. Third, optimized economics. Frugality is the core principle of a well-architected solutions. Traditional physical AI developments require a large investment of GPU cluster on-premise. With AWS pay-as-you-go model and various savings plan, customer can easily save cost of training simulation at scale on cloud. Fourth, robust security and compliance. When you are deploying a physical AI system for a healthcare facility, manufacturing plant, or a public space, security is foundational. AWS offers an enterprise-grade security for you to build an end-to-end encryption, role-based security model, granular access control to offer a secure and compliant physical AI systems. And finally, unified edge-to-cloud architecture. We can train a sophisticated model on AWS and seamlessly deploy on NVIDIA Jetson devices. AWS IoT services is really closing the gap between cloud and edge infrastructure. I hope you are excited to see a short demo of our humanoid robot, fully developed using NVIDIA Physical AI Stack on AWS. Welcome to our AWS GenAI Lab at HQ2 in Arlington, Virginia. We are buying an item from a fake website. As soon as the order is placed, the control plane agent receives the signal and triggers multiple AI agents that performs different tasks, such as path planning and inventory search. Ladies and gentlemen, welcome our humanoid robot, Storm. The fine-tuned Groot N1.5 model is running on NVIDIA G6 EC2 offering, providing a vision language action model to perform pick-and-place tasks. This is the place where we are running the task validation. Once the task validation is successful, we identify the nearest delivery workstations, the empty container, and drop the item in the box. I hope this demo inspired you to build your next physical AI system. Please do check out our AWS guidelines, including the complete reference architecture for building a physical AI with NVIDIA and AWS. Join us this afternoon if you like to go hands-on on our session IND 403 for physical AI, for building a physical AI with NVIDIA and AWS. Hope you enjoyed our session. We have a humanoid demonstration in this room, so feel free to engage and ask.